Welcome to this video in which we will discuss the spectral properties of some special cases. The spectrum of a real sinusoidal signal xt, which consists of DC and the sum of n sinusoidal components, has a special property which can be derived as follows. When writing such a signal xt as a sum of phasors, it follows that the complex numbers, which represents the amplitude and phase, of each frequency fk and minus fk are complex conjugated versions of each other. Thus, the spectrum of such a signal consists of one real component, DC, and two n complex components and frequencies. By introducing the complex number xk is ak e to the power j phi k, we can write the contribution at f0 as a real number x0 is a0, while the contribution of all positive frequencies equals half the complex number xk. The contribution at negative frequencies, minus fk, is equal to the complex conjugated versions half xk star. Thus, the spectrum of such a real signal can be described as two-sided spectrum which consists of two n+1 components. The contribution at frequency f0 is equal to a real number x0 is a0. The contribution at positive frequencies fk equals the complex number half xk is half ak e to the power j phi k, while the contribution for negative frequencies, minus fk, is equal to the complex conjugated version half xk star. This implies that the amplitude of such a real signal is symmetric. The amplitude is the same for positive and negative frequencies, while the phase is anti-symmetric. For negative frequencies, the phase equals minus the phase of positive frequencies. In many real-world signals, the frequency is not constant, but it can change. For such so-called non-stationary signals, we still can use the spectral representation as a sum of sinusoidal signals, but now we have to add one extra dimension to the spectral representation. This extra dimension represents the evolution of time. Usually, for such cases, the amplitude is represented by a color. The left-hand figure represents such a spectrum of a scale, which sounds as follows. The right-hand figure represents the spectrum of a whistle, which sounds as follows. From both sounds, it's clear that the frequency content changes with time, which is indeed clearly visible in the spectral plot. Finally, we will discuss into more detail the special case in which a signal consists of the product of two sinusoidals. First, we will show how we can find the spectral content of such a signal by writing the product as a sum of sinusoidals. Then we will show how the sum and product of sinusoidals are related in general. And at the end, we will discuss two practical examples. We can find the spectral content of a signal which consists of a product of two sinusoidal components by applying the following steps. In the first step, we use Euler for each of the sinusoidal components. The product can now be written as a sum of four terms. The frequency of these four terms can be found as the sum and the difference of the original frequencies. In this example, 200 minus 20 is 180 Hz and 200 plus 20 is 220 Hz. By combining appropriate frequencies, it follows that we can write a product of two sinusoidal components as the sum of two other components from which the frequencies can be found as the sum and difference of the two original frequencies. Thus, the spectrum of the original product contains four phasor frequencies, which represent the sum and the difference frequencies. The plot of the original signals as a function of time are depicted in the left-hand figure. The upper plot represents the separate signals and the lower plot represents the resulting product. From these plots it follows that the product is most clearly displayed by the plot of the product as a function of time, while the plot of the spectral content is most clearly to display the sum. Furthermore, the low frequency causes the envelope in the plot of the product as a function of time, which results in the fade-in and fade-out of a signal. In music, this phenomenon is called beating. From the previous discussion, it follows that we can write a product as a sum of sinusoidals. This will also hold the other way around. So let's start with the sum of two sinusoidal components with frequency f1 and f2, with f2 larger than f1. The figure gives the spectral plot. In order to write the sum as a product, we introduce two new frequencies, namely the so-called carrier frequency Fc, which is the average of the frequencies f1 and f2, and the difference frequency f delta, which is the difference of both frequencies f1 and f2 with the carrier frequency. So we can express both of the frequencies f1 and f2 as the difference and the sum of Fc and f delta respectively. By applying Euler, it follows that this results in the given product of sinusoidals with frequencies Fc and f delta. Now we will give two practical examples where we use the fact that the product of sinusoidals can be written as a sum and the other way around. As mentioned before, musicians call the fade-in and fade-out mechanism beating. They use the beating phenomenon to calibrate the pitch of an instrument. This is done by playing at the same time both the frequency of the instrument that has to be calibrated and an external sound which produces the exact frequency. As long as the frequency of the instrument deviates from the exact frequency, the sum of both sounds as a beating sound. The following sound is an example in which the exact frequency is a pure tone of 660 Hz, while the deviation of the other tone changes from 12 Hz to 0 Hz. Another application is amplitude modulation, abbreviated as AM. A message signal MT with relative low frequencies cannot be transmitted over a long distance. The plot shows the spectral content of a signal which consists of DC and one low frequency. In practice, the message signal MT consists, for example, of audio, which contain frequencies up to maximal 20 kHz. When signal MT needs to be transmitted over a long distance, it is typically modulated with a carrier frequency Fc, from which the frequency is much higher than the frequencies of signal MT. Since the product can be written as a sum, it follows that the spectrum of the resulting signal contains two identical shifted versions of the spectral content of signal MT. From the plot of the amplitude modulated signal as function of time, it can be seen that a low frequency content of the message signal MT is represented in the amplitude. This ends this video in which we discuss the spectral properties of some special cases. Thank you for your attention.